Welcome back, everyone, to a lecture series on molecular simulations and statistical mechanics. So in the last lecture, we looked at the conservation laws, which were some elegant applications of the Lagrangian. Now, the Lagrangian, as we've seen, is an extremely useful formulation of classical mechanics that we can use for a lot of different applications. However, we are now going to go into the next layer of classical mechanics, which will be Hamiltonian mechanics. The reason for doing this is we want to take the independent variables of the Lagrangian and write them with respect to different variables. So in this lecture, lecture 6, we are covering Hamilton's equation of motion. Now recall, for the Lagrangian, that the dependence of the Lagrangian was on the generalized positions, which these generalized coordinates I'm calling Q. So Qi is a generalized coordinate. So remember, it depended on the generalized coordinates of the system, as well as the generalized velocities, the Qi dots, Qf dot, and then time. And just recall that the Q dots are the generalized velocities. So when we constructed the Lagrangian, we constructed it in such a way that it had this explicit dependence on coordinates and velocities. The goal of deriving the Hamilton's equation of motion is going to be to actually rewrite L in terms of some new function, which we'll call h. And the dependence in h, we're going to now make the coordinates and the momenta, P1 through Pf, and time. Now recall that the momenta we defined from the Lagrangian as being equal to the partial derivative of the Lagrangian with respect to Q dot. And we kind of gave a general argument. Imagine you have one particle moving. Its kinetic energy is 1/2 mv squared. Let's write it in terms of the Q's and Q dots. Let's say you have a particle moving. It has no potential energy part. So its Lagrangian is just 1/2 mqi squared. If this is your L in this system, well, just take the partial derivative with respect to qi and you obtain 2 comes down mqi dot. Well, this just looks like m mass times velocity, which we know and understand conceptually as being equal to the momentum. So really, these momenta are derivatives of the Lagrangian with respect to its original variables. So the question now is, how do we go from here to here? And there's actually a mathematical trick or a mathematical formulation that is exactly designed to do this sort of procedure, to take the arguments of a function and change them into the derivative of those arguments. And this is going to be called a Legendre transform. Legendre transform. So what exactly is a Legendre transform? A Legendre transform is a mathematical tool to change the arguments of a function. We're going to say this is a mathematical tool to change the arguments of a function. Now, there's only certain functions this can work on, and we'll get into that in a second. To change the arguments of a function to the derivatives of those arguments. The best way to think about a Legendre transform as you're learning it is to look at an example, one that you probably did in middle school, which was to find the slope or find the equation of a line that is tangent to a function. So in this example, let's say find equation for a line for the tangent line of f of x. Okay, let's draw our function. Let's say we have a function that looks like this. And I'm asking you to find a tangent line that passes through this point. Well, conceptually, you know the tangent line touches the curve in only one point. So if you remember from your middle school days, maybe you draw this line. Well, how do you describe this line? It's a function with a general form, y equals mx plus b, right? Or maybe we could be more precise here, f of x equals mx plus b. Now there's a few things we know, right? We know, for instance, that we know exactly where I'm asking you to find the line, at a specific x0, right? We also, given our function, so if let's say our red function is g of x is equal to x squared, in this case, I guess this needs to be 0 for that to be true. What would we do first? Well, to find the slope here, we would just take the derivative of g. So we'd take g prime of x. Now you recall that simple exponential rule. This is just 2x, right? Okay, so that's the slope. Now what's the slope specifically at x0? Well, it's the derivative evaluated at x0, so that gives you 2x0. So now when we go back to our line, f of x equals m is the slope, 2x0x plus b, right? Well, what else do we know? We know the value of the function at this point. So we actually know f of x0 is equal to 2x0 plug in x0 plus b. Well, now all of this is known, so we can solve for b as b equals f of x0 minus 2x0 squared. And now we have our equation for the line. So just by specifying this point here and the slope, we were able to completely define this tangent line. Now, in general, if I asked you to look for any tangent line, what would you do? Well, you'd follow this exact procedure. You'd say, my line has this form. You would solve for m by taking the derivative. Let's say your other function was g of x. You'd say m is equal to dg dx. And I'm going to use partial derivatives because it's possible for our function to maybe have more dependencies here, let's say. Partial g, partial x, evaluated at wherever you're looking for the line. Then you just evaluate the function at x0, wherever you're looking for your line. Plug this m in, plug in your x0, solve for b. So this is step 1 is find slope. Step 2 is find intercept, which is b. So we're looking for this guy here, and then b. And once you have those, you've fully specified your line. Specifying lines seems like a pretty easy task, Well, where does the Legendre transformation come in? So let's draw a function again. And let's say we have this guy here. What if I asked you to find tangent lines at every single point? What would that look like? So let's draw some tangent lines as if they were at every point here. And I'll just choose a few points along the curve, and I think you'll see where I'm getting here in a second. So I don't think we need too many. But we'll draw our first tangent line, and our second one, and our third one, and our fourth one. That one's a little off. We'll just make the point bigger and just make it seem like I drew it right. So you have something like this, where you actually form what we'll call an envelope of tangent lines. Now I ask you, if I gave you the original function, let's say that our original function is f of x. If I gave you the original function, you would know everything about the function, right? You'd have its functional form and this red line. But what if I didn't give you the red line? What if I only gave you this envelope of tangent lines? Well, conceptually, you can look at this this picture and see that these tangent lines are actually carving out this curve. In a sense, they contain all of the information of this original curve, but now they're written in terms of derivatives, right? So this is where we're getting at with going from our Lagrangian to our Hamiltonian. We're actually going to construct these tangent lines, which just so happen to have a slope equal to the momenta when we look at the Lagrangian specifically, and the intercepts now, this b that we found earlier, these are going to be your Hamiltonian. H. So your intercepts are going to be the Hamiltonian. Your slopes, so your m's here, are going to be your momenta. I guess I should be more explicit that these are vectors. So let's kind of see how this works. So basically, within our Lagrangian, L, which is a function of the generalized coordinates, and I need to make sure I make these vectors in generalized positions. What we're going to do is perform a Legendre transform on these coordinates, on the velocities. So within the Lagrangian, right, we have all of these velocity dependencies. And of course, this is a very high dimensional, in practice, this is a high dimensional space of however many, twice however many particles are in your system. Whereas here, I've just drawn a one-dimensional case, or this simple, easy to visualize graph. But what's so cool about the Legendre transform is that because you're dealing with derivatives, which are linear operators, you can actually do this independently on each of the variables. All right, so returning to our Lagrangian here, we have the Lagrangian written in terms of the positions and the velocities in time. Now, let's say that we're going to do a Legendre transform over the velocities here. So the first thing we're going to do is find our slope. Well, the slope is the momentum, and it's equal to partial L, partial QI dot. That was step one of finding these tangent lines, right? And of course, we're going to do this over all the particles. Now, of course, when you look at this momentum, you could think this momentum is now written as a function of L, which is a function of the velocities. I'm going to use the notation to the f to express that there's f, generalized coordinates, q dot f in time. Now, of course, in general, we could take this function and we could solve for the qf dots as a function of the pi's, right? So we can find a function qf dot, which is a function now of the qf's and the pf's in time, right? So we're just flipping the equation around, rearranging it to solve for these qf dots. Okay, now let's find our intercept. Well, if you recall, the intercept, we just took a line and we subtracted its evaluation at a specific point. So what we're going to say then is that our new function h, or our intercept, is equal to L minus, right, because we're evaluating L, we're going to say this is equal to L minus the sum over all the possible qi dot, right? The sum over all the possible particles in the system, right, of the momentum times the qi dot, right? This is y minus mx equals b. So this is exactly how we solved for the intercept before. So remember, we solve for the slope, we invert it, right? And then we solve for the intercept, and we call the intercept h. Y is just our original function. The slope was just our momentum, and the qi dot was the x along this direction that we were taking the Legendre transform with respect to, right? Now, for convention, we're actually going to take this and flip its sign. Now, can you guys just for a minute recall what this looks like when we flip its sign? So let's write, like, let's say we'll denote this by h hat now, maybe this one written this way. And we'll now denote by h, which is the Hamiltonian, and we're just going to change the sign, so multiply these all by -1. That h now, which is equal to minus h hat. So minus h hat is equal to h, which is now equal to the sum, f I equal 1, of the momenta times the velocities minus L. If you recall, this looks like our energy function that we derived or defined earlier in the class. This h we are going to call the Hamiltonian. So let me put that here. H is the Hamiltonian. So all the Hamiltonian is constructing this set of intercepts from the tangent lines of the Lagrangian and rewriting it in a new form. H equals pi qi dot minus L. So we've just uncovered that through a Legendre transform, the Hamiltonian is equal to the sum of the momenta of each particle times the velocity of each particle minus the Lagrangian. Now let's use this equation now to derive the Hamilton equations of motion. You would expect that if the Hamiltonian contains all the information in L, that we should be able to find differential equations to do time integration of these equations of motion. Now, how are we going to do this? Well, the first thing let's do is let's look at the total derivative of h. Recall that the total derivative would be written as dh, so a change in h. Now, if h changes, there's all these different variables it can change in. We have to keep track of all of the variables, right? So it's possible for P to change, for Qi to change, or Qi dot to change, for L to change, right? So to do this, we actually need to do some product rule here. So our change in H is going to be, of course, over all of the particles. We might have a change in Qi dot and no change in Pi. So we say, okay, Pi times the change in Qi dot. Plus, we have a change in, let's say, in Pi now, from our product rule, and no change in Qi dot, right? So this was just the product rule. And then, of course, we can have a change in L, minus dL. So this is just the change in the Hamiltonian with respect to all the other variables. To proceed, let's look at what dL is. So recall that L is a function of the velocity, or the positions, the velocities, and time. So what is dL? dL is related to, in the same way, all of these changes, right? All of these different contributions from the function. So what dL is going to be equal to is, from all of these contributions, we're now going to use the chain rule, where we're going to have changes in L with respect to the positions, the Qi's, so partial L, partial Qi, times dQi, right? We're also going to have contributions from the Qi dot, partial L, partial Qi dot, dQi dot, and then, of course, changes in the Lagrangian in time, partial L, partial T. So I'm just going to rewrite this guy up here. We have dL is equal to the sum f I equal 1 of partial L, partial Qi, dQi, plus partial L, partial Qi dot, dQi dot, plus partial L, partial T. Now, can we rewrite this in terms of other variables? Well, partial L, partial Qi dot is just Pi, right? And partial L, partial Qi dot, or partial Qi, is equal to, from the Lagrange equation of motion, the time derivative of partial L, partial Qi dot, which is equal to the time derivative of the momentum, which is equal, we'll say, to Pi dot, right? So now we have that this is Pi dot. So I'm going to erase this little math we did here and rewrite our dL as being equal to the sum from f I equal 1 of Pi dot dQi plus Pi dQi dot, and this is, of course, all in the sum, plus partial L, partial T. All right, so I'm going to rewrite all this. It's very difficult to keep track of all this on one whiteboard, so just bear with me. Let's go back to our original DH. And remember, we had that this was the sum from I equal 1 to f of the Pi dQi dot plus Qi dot dPi minus dL. And then we just solved for dL. And we now have this guy, dQi dot plus Qi dot dPi. Now let's do minus dL, which we found to be minus the sum from f of I equals 1, pi dot dqi, right, plus pi dqi dot. And I think before I forgot to include this dt on the partial L partial t. And of course we're subtracting everything, so this should be minus. Well, we can actually combine some like terms here, right? Because we have a pi dqi dot and a pi dqi dot over the same sum. So these are going to have a plus pi dqi dot and a minus here, pi dqi dot. So those are going to cancel out, and we're going to be left with that dh is equal to the sum from f I equal 1 of qi. And I'm going to drop this vector notation because we're going to say these are generalized coordinates, right? So just in general, qi dot dpi minus pi dot dqi. Oh, I just said I was going to drop that. Minus partial L partial t dt. Okay, this seems pedantic. But all we're doing is rewriting dh in terms of some new variables. And we're going to see why this is important in a second. All right, so the next stage is recall that our h in general, right, is a function of qf, pf, and t. So now let's take dh of this. Well, we kind of have exactly what we had before when we were talking about the Lagrangian, right? We take the sum from I equal 1 to f of partial h, partial qi, dqi, plus partial h, these are just chain rules on each of the variables, pi, dpi, plus partial h, partial t, dt. Right? And this was dh, right? I forgot the d. But this is also dh. So these are equal to each other. Well, now we can do something cool. We can actually start to look by inspection and see what each of these terms mean as a function of the Hamiltonian. So let's look at this one first. We have a dqi, and that's shared with this term. Well, by inspection, we see that minus pi dot should equal this. So we're going to consolidate this information over here. So we have for our first relationship that partial h, partial qi is equal to minus pi dot. Okay, so we've kept track of those two terms. All right, what about the other terms? Well, here's a dpi, here's a dpi. So qi dot has to equal partial h partial pi. Partial h partial pi is equal to qi dot. And lastly, dt, we see that partial h partial t is equal to minus partial L partial t. Minus partial L partial t. This set of relationships that we've just drawn this comparison between, so I believe it was kind of crisscrossed here. This set of relationships, by looking at dh from different directions and plugging in the definition of the Lagrangian and its derivatives, gives us the Hamilton's equation of motion. Hamilton's equations of motion. So that's these guys right here. And you can see these kind of just fall out of the definition. By doing some clever mathematics and some derivatives with a Legendre transform, we can get this entirely new set of equations. The last thing I want to talk about today is something known as the Poisson bracket. And this is going to appear in both classical and quantum mechanics and be a really useful way to think about what are known as dynamical variables in terms of the Hamiltonian. So when I say a dynamical variable, what do I mean? A dynamical variable is some variable that is a function of the generalized coordinates, the generalized momenta, and time. So this could be anything. You know, the Hamiltonian was a dynamical variable. It had the same dependence. But now we're giving some more generality to the problem and saying any dynamical variable that has these dependencies, so any function. Now what happens when we take the time rate of change, the dA dt of some dynamical variable? Well, we're just going to use the chain rule here, right? So we're going to have partial A, partial QI's, so the derivative of this, times the derivative of the argument with respect to time, right? We have this time derivative now, so our chain rule now has this. Recall before we just had something like dqi, when it was just the change in A, the total change in A. But now we have the total change in A with respect to time. We need to put in this time derivative on qi. Then of course we have the additional term, partial A, partial pi, times partial pi partial t. And then the final term, partial A partial t. Right? Now we can do something kind of cool here. We can take our Hamilton's equations of motion and we can actually rewrite these terms. So we have, for instance, that in the first equation in our list, that the partial derivative of h with respect to qi is minus pi dot. Well, this here, this is pi dot, right? So we can replace this entire term with partial h, partial qi, and then of course having the negative sign. What about partial qi, partial t? Well, that's just qi dot, which is equal to, according to our second equation there, partial h, partial pi. So now we can entirely rewrite this time derivative in terms of the Hamilton's equation of motion. We have, consolidating, that dA dt is equal to the sum overall of the particles of partial A, partial qi, partial h, partial pi, minus now partial A, partial pi, partial h, partial qi. And then of course, plus partial A, partial t. So now we've written the time rate of change of our dynamical variable in terms of the Hamiltonian and the Hamilton's equation of motion. This equation here is where we introduce a definition. And what we're going to do is we're going to call this entire sum here. This is going to be defined as, so this sum, qi partial h partial pi minus partial A partial pi partial h partial qi, this sum is going to be defined as the Poisson bracket, so this curly bracket, of A with H. So this is the definition of the Poisson bracket. So what we're going to be able to do is we're going to be able to write dA dt is equal to the Poisson bracket between A and H plus partial A partial t. Now, by definition, if dA dt is equal to 0, then what do we know about A? Well, we say that A is a constant of motion, right? So if dA dt is equal to 0, we'd say that A is a constant of motion. Notice, that does not mean that partial A partial t, or partial A partial t is 0, right? Partial A partial t could be non-zero, and we could still have a constant of motion if this term canceled it out, right? So this partial A partial t being 0 is not enough. The Poisson bracket of A and H plus partial A partial t must be 0 for A to be a constant of motion. The last thing I want to look at is let's look at the dynamical variable H, the Hamiltonian. So of course, the Hamiltonian is a dynamical variable because it can be written in terms of the generalized positions, momenta, and time. Now let's look at dH dt. Well, we know that the time derivative, or the time rate of change, of a dynamical variable is just the Poisson bracket of that variable with the Hamiltonian, so in this case it's H with H, plus partial H partial t. Now, this quantity is interesting, right? If we express everything out, what we're going to find is that the first term is going to be a positive term, and the second term is going to be a negative term, but they're going to be equal, right? And you can do this exercise yourself. It's quite simple if you just write the definition of the Poisson bracket. But this is going to be equal to 0. So what we're left with for the time rate of change in the Hamiltonian is that dH dt equals partial H partial t. Now, in order for this to be a constant of motion, it must equal 0. But if dH dt equals 0, since the Poisson bracket of H with itself is 0, that means partial H partial t must be equal to 0 for H to be a constant of motion. Now, if partial H partial t, if partial H partial t is equal to 0, so if the Hamiltonian is a constant of motion, then the Hamiltonian is equal to the energy of the system. So the Hamiltonian is describing the energy. If partial H partial t is not 0, then the Hamiltonian is not the energy in this way, or it's not conserving energy. It's not a constant of motion. So today we've gone through the Hamilton's equations of motion, which are going to be what we're going to rely on for molecular simulations and quantum mechanics going forward. And we've also seen some interesting properties of the Hamiltonian, specifically when it conserves energy and when it does not. So thank you all very much for listening, and we'll see you next time.